Now, next, current. It's chapter 27, and let's try to introduce somehow current. Why I post you will see you will understand in a second. Okay, so first let's introduce the idea of current, sort of conceptually, and what in the book calls a model of conduction. And at this point, every time I feel awkward, because now I have to tell you, I have to confess. It's sort of, I'm supposed to say something like, okay, bless me, Father, for I have sinned, right? I lied to my students, right? And of course, where did I lie, right? And why? But actually, I didn't lie completely. I just didn't tell you at some point the whole truth. And it makes sense sometimes from educational point of view when it's not a good idea to reveal the whole story. It's better to reveal it in layers, right? Then maybe it's easier to for your brain to accept it. Although in this case it's not a big deal. But anyway, so we present it in a layers. But anyway, so where did I lie to you? Or where I didn't tell you the whole truth? You remember when we discussed properties of conductors in the electrostatic equilibrium? You remember what I told you? If I told you this, so if you, for example, take a piece of a conductor and expose it to some external electric field, or maybe dump some amount of charge in the conductor. So then what happens? First, there will be a mass in the conductor, right? Because electrons will start running like crazy in order to achieve what? In order to achieve what is called a static equilibrium, when the electric field inside of the conductor is zero. And what else did I tell you? Did I tell you about electrons in the electrostatic equilibrium? They stop running. You remember I told you at first they run like crazy, and then once they manage to make electric field zero, they settle down, they buy a house, get married, and live happily ever after, right? And I told you that they don't run anymore. It's not completely true. It's not completely true. So let's see what actually happens when they reach this electrostatic equilibrium. What do they still actually do? Okay, I took this picture from the book. It's basically, you see a crystalline structure of some metal, right? Okay, oversimplified version, right? So you see, you have this red atoms, basically charged atoms, because they lost some electrons. So now these atoms are charged, and we call them ions, positive ions, right? And of course, between them, there are tons of space, and of course, tons of free electrons, which can fly and move around, right? And now, since any piece of a conductor in our life, in our experiments, they are, okay, most of the time they are at the room temperature. Or we can say they definitely above the 0 Kelvin, right? And whenever an object conductor is above 0 Kelvin temperature, okay, let's say at room temperature, it has thermal energy. It has thermal energy. And for electrons, which are teeny tiny, right, that thermal energy is gigantic, really gigantic. As a result, these electrons, they actually don't just sit somewhere and don't move, as I told you, right? They actually have a gigantic velocity, really gigantic, really large velocity. But let's pick one electron and try to follow it to understand what actually happens. But for now, we assume that electric field is not applied. There's no potential difference across this conductor. Just piece of a conductor at room temperature has thermal energy. As a result, electrons move like crazy. But let's pick one electron and see what it does in time. And try to see what its maybe average velocity over some finite period of time. So let's say, for example, where is this? You see this green dot? Green dot. It's the beginning, okay, the first point of this electron. So first, because of the thermal energy, it has gigantic velocity flying that way, for example. So sooner or later, because it flies through the crystalline structure, it is going to collide with one of these ions, positively charged atoms. Of course, after collision, it changes its direction, quickly gets accelerated, and will fly in a different direction. Let's say this way. Again, with a gigantic velocity, and of course, sooner or later, it will collide with another ion. Again, it will change direction, start flying that way. And then again collision, then it will start flying this way, then that way. And so you see, it keeps bouncing, And if you look over a finite period of time, you will realize that this electron, yeah, it flies with gigantic velocity, but all the time it exists in this, for example, volume of the conductor. It doesn't drift in any of the directions. So it just randomly, like crazy, runs around in this volume without any definite movements in a certain direction. So as a result, when I told you electrons don't move, I was partially correct, because if you look, for example, over this volume, yeah, so electron doesn't move beyond this volume, right? So it's just bouncing around. It's sort of like a person, yeah, settled down, right, buy the house, but it's still maybe it doesn't travel globally, but it lives around, right? So it travels to the store, to work, right? So for something else, visiting friends. So every time it travels locally, right? But still settled down. The person settled down, right? So the same electron, it settled down within this volume, right? So I didn't completely lie to you. But I didn't tell you the whole truth. But again, as I told you, from educational point of view, it makes sense. You can justify that. It's easy to present in pieces, information in pieces, right? So in this case, there is no any drift of these electrons in a certain direction, right? So if you look, for example, at the average velocity of this electron over a finite period of time, it will be basically zero, right? Okay, now let's change conditions. What if we apply potential difference or electric field in this conductor? And as a result, the situation will be somewhat different. Okay, so this is basically the same thing. Again, I took it from the book, right? So you see, now it's the same basically crystalline structure, but now we have electric field. You see electric field lines, these red lines, and they point this way towards me, to the left. So since we are observing an electron, which is the negatively charged particle, of course, that electron now is going to experience electric force. And of course, that electric force is going to act on the electron in the direction opposite to the direction of the electric field, because the charge is negative. You remember, force is in the opposite direction. So it is going to experience force that way. As a result, it is going to experience some additional motion in that direction. So since there is a force in that direction, of course, electrons will start experiencing additional acceleration on top of the thermal motion. Additional acceleration, of course, there will be additional velocity. So now we have two velocities. One, because of the thermal motion, that gigantic velocity is still large, it's still there. Our conductor is still at room temperature. But now we have also on top of that gigantic velocity, we have a small velocity, reasonably small velocity in that direction. As a result, if you superimpose these two velocities, you will get trajectories like what is shown in the picture. You see, now instead of straight lines, electrons travel along parabolas. Right? Still with the gigantic velocity, thermal velocity, but now also there is a drift of electrons in that way. Again, in the direction opposite to the direction of the electric field. So this additional drift, and of course, if you compare these two velocities, thermal velocity and this drift, thermal velocity is way, 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 way larger, right? But anyway, this drift of electrons in that direction, that's what we call current. That's what we call current. So that's basically microscopic description of current. So if you basically dive inside of the conductor, that's what you would be able to see if you could dive inside of the conductor. Right. So, okay, that is an introduction of the current on the level of, again, blah, 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 conceptually, right? But again, since we are all a science major, we need to define current properly using expressions so that we can be quantitative, so we can compare currents. This is larger, this is smaller, right, and so on. So now it's time to introduce actually some expression which can be used to define current. Okay, now actually definition of the current. And you know what? Definition of current is absolutely normal, absolutely logical. It's sort of if you okay, imagine this situation. I will just tell you that even if somebody asks you to define current, you would introduce it in a very similar way. Let's imagine this situation, you know, spring, April, and I know you got bored and you decided to go to Boston to watch Boston Marathon, for example, right? And of course, the best place to watch it, it's at the top of Heartbreak Hill. It's right next to Boston College, right? Because their runners is basically dying, right, suffering, right? And there you can sit with it in a chair, right, with some cocktail, right? And you can, I know, enjoy people suffering of people, right? And let's say you get bored even there. And so you decided, and let's say you decide to introduce current of runners, right? For fun. How would you do it? Of course, you would do it something like this. You would imagine a line across the street, right? Sort of like a cross section across the street. And you will take your watch and start by looking at the okay, and you will start counting number of runners crossing that line, imaginary line, and while you watch at your watch. Oh, yeah, while you measuring time. Right? So let's say you measured, I don't know, 500 runners in, I don't know, 50 seconds. So how would you introduce current, in this case, current of runners? You will take number of runners and divide it by the observational time. 500 divided by 50, it will be what? 10 runners per second, right? So in this case, it will be your current of runners averaged current over what, 50 seconds. But of course, you can start reducing the observational time. You can measure it over, I don't know, 10 seconds, let's say, I don't know, 50 runners. So you will get average current over 10 seconds. It will be 5 runners per second, right? You can make observational time smaller and smaller and smaller. And of course, the smaller you take observational time, the closer your current of runners is going to be to the instantaneous current of runners, right? So idea behind, okay, that's why I took this picture, right? That's why I created this picture. So idea behind electrical current is exactly the same. The only difference, runners, when they cross your line, they, okay, let's say about masses. Of course, they have different masses, right, for example, right? But in electrical current, what are we going to measure? We're going to measure or count number of electrons crossing some cross-section. And we also know that all electrons are identical. Not like runners, they have different, in different shape, different mass, different mood, whatever, everything is different. But electrons, all identical. So we know their charges. So if one electron cross, we know that 1.6 times 10 to the power of minus 19 coulombs crossed your section. If 100 electrons cross your section, you can tell immediately what will be the total charge which just crossed your section, cross-sectional, your cross-section, right? So now, instead of actually counting a number of electrons, like what we did with runners, now it's more convenient, it's better to measure the total amount of charge crossing a section. Make sense? Because now we know each electron carries this exactly the same amount of charge. So now we're ready to actually introduce current. So by definition, it's the total amount of charge, right? Again, each electron carries a certain amount of charge. Of course, we can introduce the total amount of charge. and divided by the observational time. If you observed over a infinitesimally short period of time dt, so that's the amount of charge which crossed, for example, this cross section of the wire, right? So let's say all these electrons, and each of those electrons carries, we know which amount of charge, 1.6 times 10 to the power of minus 19. So this total amount of charge in this volume in the period of time dt is going to cross this imaginary cross section. So now, every time, whenever you measure the current or you want to introduce the current, you need to imagine, okay, some cross section, and you can say, so I'm measuring current at this cross section. So this amount of charge cross this cross section, and if you divide it by the by the observational time, you'll get the current. So that's what current, okay, in this case, it's an instantaneous current, right? Current measured over infinitesimally short period of time. But of course, we can introduce also average current over finite period of time, right? Over finite, let's say, 5 seconds, 10 seconds, 50 seconds, right? 5 milliseconds. And of course, in that case, we're going to talk about not a dq, but some finite amount of charge, some q, 5 coulombs. Okay, so that's how current is introduced. Absolutely natural introduction. Nothing weird. Everything in physics is natural. Right. Okay, so now we introduce new quantity. What about special unit? Of course, the next question. Should we introduce a special unit? SI unit. No doubts, yes. We have to introduce the special unit because current is used almost everywhere. Almost all people in the world using current, right, to some extent, to some level, right? And as a result, instead of pronouncing every time, I don't know, I have a current on 5 coulombs per second, it's annoying, right? It will be annoying. People will get annoyed, right? So it's better to introduce the special unit, amperes. 1 ampere, 2 ampere, and so on. So it's much more convenient. But of course, we need to keep the balance. If we start introducing the special units for each quantity, then it will be just difficult to remember. It will be just a big pile of different units, and it will be also annoying. So we need to keep a healthy balance. If a quantity used a lot, it makes sense to introduce a special unit. If it is used only by hardcore theoreticians, right, who cares about them? They can suffer, right? That's their own small world, right? So in physics, yeah, people also practical. So amperes. Okay, and now let's digress a little bit at this point and talk about amperes. Guys, you remember things like basic units or fundamental units in physics 1. It's basically a set of units. If you know them, you can construct any other unit. In physics 1, probably your instructor discussed with you, there are 3 basic or fundamental units. Which are those? First of all, kilograms, which allows us to measure mass. Then seconds allows us to measure time. And then meters allows us to measure distance. 3 basic units, fundamental units. Now, using these 3 basic or fundamental units, you should be able to construct any other units in physics 1, in mechanics. For example, newtons. What is newtons? What is inside of newtons? It's a kilograms times meters divided by seconds to the power of 2. You see? Constructed out of those 3 units. The same joules, the same watts, you can easily construct those units out of those 3 basic or fundamental units. Now we are in physics 2. We are in the electricity and magnetism, electromagnetism. Now we need to also most likely add an additional fundamental or basic unit to this set of 3 units. And that is actually amperes. Ampere is the basic or fundamental units. So now overall we will have 4 units: kilograms, meters, seconds, amperes. So electromagnetism, not very productive. It adds only 1 additional unit to the set of basic units, amperes. But of course, you know what? Logically, it sounds strange, because why not coulombs? sounds like coulombs would be more natural, right, from the point of view of physics to use as the as another basic unit. But you know what? In my opinion, why amperes was used, not coulombs? Because it's much easier to measure amperes than coulombs. Measuring coulombs, yeah, we don't have those devices, right? Of course, you can buy it, but amperes, you can just take a voltmeter, right? Switch to a certain to proper settings, right, to measure current, right? Two probes, and there is the current. So, from the practical point of view, I think that's why ampere was sort of introduced to the Hall of Fame of basic units, right, fundamental units, because it's easier to measure it, right? Okay, when you will take, or some of you already took physics 3 or thermodynamics, right? There, thermodynamics also introduce only one additional basic units or fundamental units, units of temperature, Kelvin. Usually Kelvin is used. So overall, in classical physics, there are 5 basic units of fundamental. Again, kilograms, seconds, meters, amperes, and then Kelvin. 5 basic units. The Hall of Fame. Okay, so now I just wanted to digress and discuss that. So yeah, ampere, it's a very, very important unit, and it's one of the basic or fundamental units. SI units, of course. Okay, now let's move on with current. All right, so okay, we still have 7 minutes. Okay, not much. Next logical step. Current has a direction. It's not a vector because it doesn't obey vector rules, but it has a direction, right? You all know. So, which direction should we pick as a direction of current? Imagine that we have this arbitrary circuit. We have a battery, you see, positive electrode, negative electrode. And there is some device attached, right? I know it can be bulb, it can be resistor, it can be motor, it can be anything, right? Some completely arbitrary device, let's say. And so now we need to make a decision. Which direction should we use as a direction of current? Whenever I ask students, right, of course, there are some students who are advanced and they know the correct answer. And of course, they tell me what's the correct direction of current. But let's think as researchers who lived, I don't know, 250 years ago, when all this was a hot subject in physics, in research. Imagine yourself a researcher, right? So you just introduce a definition of current, and now you need to make a decision. It's up to you. Which direction should be used as a direction of current? Because there are only 2 options, counterclockwise or clockwise. Which direction should we pick? Of course, it's difficult for me to bug you here, right, virtually. But let me express what I would feel if I lived 250 years ago. Most likely, I would analyze like this. First of all, I would think which charges actually move. We all know that positive charges, they do not move. Positive charges in metals is basically those charged atoms, right? Which are in the crystalline structure. They cannot move, right? But which particles move? Of course, electrons. There are tons of them. They are free, right? They have freedom and democracy, so they can move in any possible direction, right? As it depends on the direction of the electric field and potential difference, right? So of course we all know that electrons travel from the negative electrode to the positive electrode of the battery, because here there are crowded number of tons of electrons, they hate each other. Of course, they want to run as far as possible from each other. And of course, they run towards the positive charge. So, of course, electrons travel that way. Of course, so logically, I would pick this direction because there is an actual motion of charges. Of course, why not? Why shouldn't we pick this direction as the direction of current? For me, it sounds completely logical and reasonable, right? From the point of view of physics. But let's think from the practical point of view, really down to earth practical point of view. Where else have we seen some directions? Just recently, right, in this course. You remember electric field lines? And electric field lines, what's the directions are those lines? All the time, they start on positive charges and end on the negative charges. So basically, direction from plus to minus, right? And again, it's a consequence of the convention when we decided to use a positive probe charge, right? As a result, electric field lines all the time from plus to minus. And if we pick this direction of the current, which would be from minus to plus, so now if you work in physics in this in the world of electricity, every time you will have to remember, okay, so that is the current. So direction from minus to plus, electric field lines from plus to minus, minus to plus, plus minus, minus plus. At some point, your brain starts skipping a bit, and you will start making some silly, stupid mistakes, confusing with which quantity you work, right? And what is the correct direction? It's not a big deal. Yeah, it's not going to happen that often, but it will definitely confuse you from time to time. So it's not very convenient. It's not very practical. So from this point of view, it's better. It's more convenient to follow exactly the same convention, so that it doesn't matter if it's a direction of the electric field lines or current, all the time directions will be the same. So that if you wake me up in the middle of the night and it will ask me, so what's the direction of this? I would just, without even turning on my brain, I would tell you immediately, okay, it's from plus to minus, give me a break, right? I want to sleep, right? So from that point of view, it's better not to follow what is logical, but to follow what is practical. That's why I put this picture of Garfield, right? Right. So it's better, more convenient to introduce direction of current as the motion of positive charges from plus to minus. So direction of current is from plus to minus by convention, because again, but again, logically, it doesn't make much sense. Logically, if you understand the physics, right, of the processes in the circuit, it makes more sense to pick the opposite direction from minus to plus. But nevertheless, physicists picked by convention direction of current from plus to minus. It's a basically effective motion of positive charges, which actually, of course, do not move. They part of the crystalline structure. They cannot move. Nevertheless, we pick this direction for the current. And you know, of course, from the mathematical point of view, direction of negative charges this way, it's like a direction of positive charges in the opposite direction. Okay, so by convention, direction of current is from plus to minus, so that we would never confuse ourselves, right? So whatever direction, electric field from plus to minus, electric current from plus to minus. Don't think from plus to minus, right? Okay, I hope I convinced you, right? Yeah, I like this picture, right? It's not logical, it's just our policy. Okay, this, I'm not going to poll it, right? I just want to emphasize on one thing using this question. So let's assume that we have a conductor, piece of wire. And let's say we pick this section, cross section. You see this dashed line to measure current. And let's say we measure that every minute 120 coulomb of charge flow through this cross section. So what's the value of the current? And of course, the question is trivial. We just need to use a definition of the current. But of course, we define the current, we define the instantaneous current. So we use infinitesimally short period of time, dt. But here, the observational time is not infinitesimally small. It's every minute, 1 minute, right? So we need to use, of course, sort of the average expression for the current. You take the charge and divide that by the time of observation. So in this case, it will be, you see, q divided by delta t, not dq over dt, but q divided by delta t. And the trick is, you must, whenever you calculate or measure current, you must use seconds. You cannot use minutes or hours, because in that case you will mess up a units, and you will confuse people who would try to understand your report or proposal or whatever, right? So you must use seconds. In this case, since it says every minute, in 1 minute we have 60 seconds, so we need to take charge and divide that by 60 seconds. So the question is simple, and that's why I didn't want to poll, but I want to emphasize that, guys, use seconds, because amperes, what is amperes? It's a coulombs divided by seconds. It's not coulombs divided by meters, not coulombs divided by hours or years, right? Otherwise you will create a mess. Okay, so just be careful. And so, yeah, of course, the answer is 2 amps of current flows through this wire in this case. Okay, so now next, what else can we say about the electrical current? Conservation of current. Oh, no, current density. First, current density, sorry. So next one, current density. And definition is quite simple. Again, let's assume that we have a piece of wire, right? Again, let's say you pick a cross section, this, right, cross section, to measure this current, to measure cross section, and let's say the area of this cross section is A. And let's say you measured current I, which goes through this cross section. And so now we can introduce what is called the current density. So you take this total current and divide that by the cross-sectional area through which this current flows, right? So that's what a current density by definition. It's similar like charge density, volume charge density, for example. Yeah, you remember we took the total charge and divided that by the volume over which that charge was distributed. And of course, in this case, I tacitly assume that this current is distributed uniformly over cross section. So charge density, current density is exactly the same, right? But of course, it's not all the time true, but in that case, it will be mathematically, it will be more complicated to describe it, but still straightforward. But in this course, all the time, we're going to have a uniform distribution of current. So we can use this. So current density, by definition, that's how we define it. It's a current divided by the cross-sectional area through which that current flows. Right. And of course, then if you say, for example, let's say you have in your problem current density is given, and let's say area is also given, and you want to find current. Okay, just solve it for the current. So it will be J times A. And guys, we're going to use this a lot in a week or so when we will be in the world of magnetism, and we will start applying Ampere's law. You will have to find currents flowing through this part of the wire or that part of the wire, and we will be using this a lot. And still, lots of troubles with applying this. So, but we will practice it. So, of course, there's no point of introducing special units, right? So it's just whatever you see in the formula, amps divided by meters to the power of 2. Okay, so usually the idea is quite straightforward, simple, but there are some issues with applications, especially when the cross section has a complicated shape. For example, when there are holes, inside of that hole there is some other current. So in those cases, yes, students start struggling a lot. So now, next, conservation of current, right? And what actually lies behind this conservation of current? It's that universal law, conservation of charge. It's just the application of conservation of charge in the world of circuitry. Right. All right, and I'm going to present sort of two forms of this law. First one, where we have a wire and there are no any junction points. What does it mean? Some students ask, what does it mean, a junction point? Okay, let's say we have a piece of wire. So right now it doesn't have any junction points. At a junction point, current can be splitted, or current can be merged. For example, let's say first I have one piece of wire, but if I take the second one, and solder it over here. So now if current flows from this side, of course, it will be split, and part of that will go up and part of that will go there. So this now is called a junction point. Of course, you can have more than one junction point. You can have, I don't know, several wires soldered to the same point, right? So this is called a junction point. Right? So in the case if there is no junction point, like yeah, if I take one wire, then current will be exactly the same. It doesn't matter which cross section you pick. If you pick here cross section to measure current, let's say it will be 5 amps, or here it will be again 5 amps, or here it will be 5 amps. Current will be exactly the same. Or even if you have a more complicated situation, let's say you have still no junction, but let's say you have a wire of this shape. You see here the cross section is small, here cross section is large. And even in this case, since there's no junction point, it doesn't matter where you measure current, current will be exactly the same. So you can measure here, here, or even here, current will be exactly the same. To justify it, it's very similar to the situation when let me first open this the whole part of the slide, right? And then it's very similar to the situation with water flowing through a pipe with different cross-sectional area, right? Because it's difficult to compress water, almost impossible, right, under normal conditions, right? So then how it works? So when water flows through a part of the pipe with smaller diameter, then of course water flows faster. And of course, if you measure the amount of water per unit time crossing a certain cross section, let's say you measure 5 liters per second, for example. But when water flows through a pipe with larger diameter, larger cross-sectional area, then of course water will flow slower, but because of the larger cross-sectional area, it will still give you the same 5 liters per second, for example, right? Exactly the same story with current. It doesn't matter what's the cross-sectional area. If there is no junction point, current must be the same. Right? Usually, students remember after me bugging a few times, but I will, and of course, I will keep reminding you about this. Right? So, if there is no junction point, current will be the same. It doesn't matter which cross-section you pick to measure your current. Okay, so it's the first part of this sort of law when there is no junction point. What if there is a junction point? So you just need to look at that junction point, and here's the statement. Conservation of current. The total amount of current entering junction point in must be equal to the total amount of current leaving that junction point. It basically means that if 10 electrons enter junction point, I know, per unit time, per second, then the same 10 electrons must leave the junction point per unit time. The electrons cannot just park somewhere in the rest area and take a nap. No, no, no. They will be all pushed by the potential difference, and they cannot skip running. All right. So this is conservation of current in the presence of a junction point, right? For example, let's say again, I think I took this picture from the book. All right, let's say we have this part of the circuit, and this is a junction point, right? This is the junction point. So we have only one wire. Okay, we have this situation. So we have only one current entering junction point, I in. But we have two currents leaving junction point, I out 1 and I out 2. So if we apply this general statement for this particular situation, so it will be on the left hand side we'll have only one current, I in, but on the right hand side we have two currents, I1 and I2. Right. Okay, so usually students don't have troubles applying this, and of course in next week when we will introduce Kirchhoff rules, we will realize that this is just one of the Kirchhoff rules. junction rule, right? But of course, it's just what lies behind this conservation of charge, universal law, right? As I told you, all of this what we're doing here in the in this simple circuitry, we just apply that fundamental stuff which we developed at the very beginning of this semester. So next, what's next? I think we discussed almost everything about the current. So now it's just let's look at this question. Yeah, we'll poll it. Of course, the poll is in the chat, and then we will see what else can be introduced. So what do we have here? 4 wires, junction point. You see, 4 wires are soldered at the same point. And we have some information about currents. We know that there is a 2 amp of current entering junction point through this wire. Then there is a 5 amp of current entering the junction point through this wire. Then 9 amp of current leaves this junction point through this wire, but we don't have any information about the current in the wire number 4, in the 4th wire. So the question is, the current in the 4th wire is what? You see the value of the current and you see its direction. So which statement is correct for this case? Right. Okay, give it a try. Again, the poll is in the chat. Again, just look at the conceptual test 1. And of course, today is July 23rd. Okay, let me scroll it up to see the chat. I mean, yeah, to see the poll. Yeah, I can see that. And you started. Cool. Let me discuss the way I want to discuss this. Obviously, here we need to apply conservation of current in the presence of the junction point. Okay, 21, good. Which is, okay, let me bring slides again forward. Which is this? Again, total amount of current entering the junction point must be equal to the total amount of current leaving junction point. So now, in order to apply this properly, we have no problems identifying where these 2 amps and 5 amps and 9 amps current should be. 2 and 5 amps of current should be on the left hand side because those currents entering junction point. 9 amp of current leaves junction point, so it should be on the right hand side of the equation over here, right? But what about the current in the 4th wire? So in order to write this law properly, we need to make a decision about current direction of this unknown current. We actually need to guess. At this point, you should jump probably. What did he say? Guessing? Guessing in physics? Yeah. In this case, in cases like this, very often we're going to guess direction of the current. Because look, guys, we have only 2 options. Current can flow to the right or to the left. We have 50% of chances of just guessing it. It's a huge percentage, right? In the world of gambling, right? So of course, let's use that percentage. So in which way? We're going to, okay, we're not going to use this word guessing. We're going to say fancier word. We're going to assume a current direction, this unknown current direction, right? And once we assume a certain direction to the left or to the right, it doesn't matter. Let's just assume. Then when we write this law properly with that assumption, and when you solve this equation for that unknown current, and if your current happens to be positive at the end, this unknown current, then great. It means that you are good at guessing that direction, current direction, which you guessed was correct one or is correct one, right? So it's your lucky day, right? You are good at guessing. Go and buy a lottery, right? But if your answer at the end, the value of the current happens to be negative, I don't know, minus 5 amps, for example. So what does it mean? It means that the value of the current in this 4th wire is 5 amps, and minus just indicates that your assumption about current direction was wrong. But again, so it means that if this direction is wrong, it means the correct direction is that one. You solve the problem in either case. When you're guessing is if you guess it right or wrong, but you need to assume a certain direction, you need to guess in order to kind of smoothly go through this solution. And it's not the first place where we're going to sort of assume a current direction. We're going to do it in many places, right? Many times, several times. So let's use this trick. Let's assume a current direction. I assumed, okay, to the right. Okay, what a big deal. I assumed to the right. You could have assumed direction to the left. At this point, don't sweat, right? So just assume a certain direction in order to get through the calculations, and then at the end, you can adjust and make a statement what is the actual direction of the current. Okay, so now if we assume that current Ix, so that's how I label this unknown current in the fourth wire. If I assume that that is to the right, okay, so this is my current, assume direction, not the actual. So, but now I can write this law properly. So it means that my unknown current must be on the right-hand side of the equation, over here, next to the 9 amps current. Okay, so now 2 and 5 must be on the left-hand side, 9 and I sub x must be on the right-hand side. So now solve it for I sub x. Obviously, here was 7, here we have 7, so I sub x must be -2. Okay, so now we have to make a conclusion. So it means what? It means that the value of the unknown current is 2 amps, and minus just indicates so I'm bad at guessing. So my assumption about direction of I sub x current is wrong. So it means that my current, our current I sub x flows to the left. Problem is solved. If you assumed direction to the left, of course, your answer would be positive. Okay, you would be better at guessing. In both cases, in your case, in my case, we both come up with the same answer, with the same results, right? Yeah, 50% chances of guessing it, it's a huge percentage, right? So you can use it, and we used it just now. And again, we will use this trick many times in this course. Every time when we will have to talk about some current in some circuits, right? Okay, makes sense? So the answer, of course, 2 amps, but to the left. And yeah, most of you answer it right. Okay, still, some students hasn't responded. Okay, cannot do anything about this. So now, we introduced everything that we can about current, the electric current, right? So now next, logical. What can be next? Current, the electric current, doesn't flow through empty space, right? If it flew through empty space, then all this, there wouldn't be any point of introducing all this. But since current flows through what? Through metals, right? Through conductors. And of course, it's a solid material, right? Conductors, of course, they have some crystalline structure. Basically, a bunch of atoms are positioned at the right places, right? And since, and also all those atoms are positively charged, because you remember, conductor has tons of free electrons. Where did those free electrons come from? Of course, they ran away from their parents, from their nuclei, right? You remember those valence electrons, the outer electrons, they run away from their parents, making those atoms positively charged. And any positively charged atom is called positive ion. So basically, in a crystalline structure consists of, or crystalline lattice consists of a bunch of positive ions, right? So, and electrons must fly through that crystalline structure. Of course, they're going to experience lots of troubles flying through that material, right? It's like try to run through the forest like an electron along a straight line. Of course, you'll experience lots of troubles, right? Colliding with trees, right? So the same electrons are going to experience. So now we need to model somehow, describe somehow that painful experience that electrons are going to experience, right? So now we need to introduce somehow in our model. You remember we're just modeling the nature. So now we need to describe somehow the presence of the material in presence of the material. Okay, in the way we model the current. Okay, let's say it this way. Okay, so anyway, let's introduce the resistance. So let's imagine some piece of a conductor, cylindrical shape, right? And let's apply a potential difference, delta V. Okay, if you apply a potential difference, as a consequence, as a result, what will happen? Of course, the electric current will start flowing through the material. So the reason is potential difference. Consequence is the current, right? And so now, of course, if you're an experimentalist, of course, you will start playing with these two parameters, delta V and I, to see how they're going to respond. Okay, so if you increase potential difference, obviously current increases. If you increase potential difference more, current also will increase, right? So pretty much they're increasing together. And of course, if two quantities behave like this, then of course the natural response of the brain, natural desire of the brain, kind of, you know what, if they're increasing together, what about the ratio of these two quantities? Maybe we can get something interesting out of that. And if you look at the ratio of the potential difference versus current, you will be surprised, or maybe not surprised, but you will see that every time you will be getting exactly the same number. Of course, within experimental error, right? So it doesn't matter what will be delta V, and of course, a corresponding current. If you take the ratio every time, you will end up with the same number. Of course, assuming that you don't change the system, you don't, the temperature of the conductor, you don't change, material, right? So if you keep everything the same, then that ratio is going to give you the same number. Okay, if you're getting the same number, it's a kind of clear indication that that number is some intrinsic property of this material, of this conductor, right? No, what I said, it's not completely correct. Not the property of the material. It's a property of this conductor, of this object, right? So what do we usually do in this case? Next step, we just need to give it a cool, nice name, right? So that NSF can give us more money to do our research, right? And of course, a nice name is the resistance, electrical resistance. So pretty much that's how resistance is defined. R capital resistance of this particular object, is delta V, potential difference across the conductor resistor, and divided by the electrical current which flows through that. And it has a fancy name, Ohm's law. Okay, so now we introduce a new quantity. And so then next, of course, what about the SI unit? Do we have to introduce the special unit? No questions, yes. Because resistance is used, almost everyone in the world use the idea of resistance at some point and quite often, right? So instead of pronouncing every time volts per amps, it can be annoying, right? So if you use it a lot, so it makes sense to introduce the special unit, ohms, right? Okay, then. Yeah, of course, if you plot, for example, if you look at the IV curve very often, yeah, it's called IV curve. You see on one axis I current, on the other axis is potential difference, IV curve. It will be a straight line. Okay, so now, actually, yeah, you know what? Yeah, it's named after Ohm because he was first published his results, right? And he found this. But actually, Cavendish, British researcher. He was the first one who discovered, but he was painfully shy, and for whatever reasons he found this expression, this law before Ohm's, but for whatever reasons he didn't publish it, and only when he died, right, so in one of his drawers people found these results. But anyway, so since Ohm published it first, so the law is named after him. Then the next thing, you see, it's written Ohm's law. Is it a true law? You remember what I usually called a law, especially at the very beginning of the semester when we were introducing almost every class a new law, of new fundamental equation. You remember what we call law? Law, it's basically a fundamental equation which can be applied at any point of the universe, at any moment of time, by anyone, right? It's not like laws, our human laws, right? You can be outlaw in the United States, but you can be okay, nice citizen in, I know, in Mexico, for example, right, or somewhere else, right? So our human laws, yeah, they depend where you live. It depends where you live. But laws of nature, right? They don't have true laws, fundamental laws of nature doesn't have boundaries. You can apply them anywhere you want. But so that's what we call law, and of course fundamental equation. But what about Ohm's law? Is it a true law? No, no. It's just a basically we can say it's basically experimental expression which happens to work among conductors only. Even, for example, what if you look at the IV curve of a diode? You know diodes, right, in semiconducting material, right? So IV curve is much more complicated. It has some sort of exponential dependence, right? Or even if you just look at the incandescent bulb, when it gets too hot, dependence between current and the potential difference is not a straight line. It starts sort of reaching saturation. So Ohm's law is just an experimental expression which happens to work for metals. Right? So strictly speaking, we shouldn't be calling it a law. And that's why I put this picture a liar. Right? We shouldn't be calling it law. It should be called somehow else. But I guess out of respect to those people who introduced it first, right, who found, and back then maybe they thought that this is a fundamental law. Right? So it's still, we still call it law, but strictly speaking, it's not a law. Okay, anyway, it's sort of philosophical short discussions, right? So anyway, it's not that important, right? As long as we know how apply it, and as long as we know that it has limitations. Right, so next. What's next? Oh, now, nice question for you. Next one. So what do we have here now? We have, you see, piece over circuit, right, with a resistor. Actually, this is a symbol which is used to show resistance in the circuit. For me, every time when I try to draw it on a piece of paper or on a whiteboard, every time it looks ugly. So I'm not a big fan of this symbol. I actually like a symbol which is used in Europe, just basically a sort of elongated rectangular. It's much easier to draw nicely, right? But every time when I try to draw this, it looks ugly. Right, but anyway, so this is the symbol which is used to denote a resistor. And let's see, we know the direction of current which flows through this resistor. And there are 2 points, A and B. So which point is at higher potential? If we see this information, we should be able to tell which point is at higher potential. Is it point A or point B? And this is, again, the poll number 2 in the chat. You can, you see that. Okay, give it a try. So now let me discuss this. Okay, so in order to answer this question, Let's recall a direction of current. Our assumption. You remember yesterday and also at the beginning of today's class, I reminded about that. Uh, Current by convention flows from plus to minus, so from the positive electrode of the battery to the negative electrode of the battery, right? Okay, so I think I have a small picture over here. Yeah, so that was our current convention about the current direction. So it means it flows from plus to minus, and which electrode, positively charged electrode or negatively charged electrode, is at higher electric potential. Obviously, positively charged electrode, because points on that electrode are going to have positive electric potential. Points of the negatively charged electrode are going to be at the negatively will have a negative potential, right? So of course, electric potential of points around a positively charged object all the time is at higher potential than points around a negatively charged object, right? So it means that current, by our convention, flows from areas with higher electric potential to the areas with lower electric potential, from plus to minus, from higher potential to the lower potential. So now, whenever you see direction of current, you should be able to tell immediately. So over here, these are points at higher electric potential. Those points are at lower electric potential, because again, current all the time flows from plus to minus. And we're going to use it in the near future. And I just wanted to emphasize on that, right? So if you see direction of the current, you should be able to tell immediately. Here, sort of plus, it means higher potential. There, minus a lower electric potential. Right. Okay, I just wanted to emphasize on this important thing. We're going to use it when we start analyzing simple circuits. Right. And I think you will need it in this homework. There will be okay, I don't remember the number, but I think they will be given these are points at higher potential, these points at lower potential, and of course you need to conclude immediately that current flows this way, right, in order to write properly conservation of current. Right. But after this, you should be able to answer that question by yourself. Great. So now next. Okay, 22 responses. Okay, great. Somebody came back. Next question, of course, I'm not going to poll. I just want to discuss it. So the same picture. What can you say about the electrical current? Is the current greater at point A or point B? But of course, at this point, everyone should be able to answer, because I already said many times that it does. If you don't have a junction point, and that's what we have here, there are no junction points. If there are no junction points, or there is no junction point, then current must be exactly the same at any point. It doesn't matter which cross section you take, this, or that, right? So current must be the same. Conservation of current without a junction point. You know what? I need to turn off my fan. It blows air at me and my eyes are getting drier. Okay, yeah, and it's quieter, at least for me. Of course, you don't hear that, because this is the filter can filter out any periodic noises. So in this case, the answer is C. The correct answer is C, but of course, we're not going to bold that. So what's next? Now, yeah, we introduced the idea of resistance to describe the presence of the conducting material. So to tell that actually our current flows not through an empty space, but through crystalline lattice, crystalline structure. So now next, let's look inside of this R. Let's look at its anatomy, right? So let's see which parameters it can depend on, right? So for example, let's say I want to calculate R. let's say I don't have a ability to measure potential difference, and I don't have ability to measure current in order to get this experimentally. So how else can I calculate R? Maybe R depends on some quantity, some parameters, and if we know that information, maybe we should be able to calculate R somehow else. Basically, let's look inside of R to see its internal structure, right? And we're not going to derive it, although, yeah, there are some derivations in the books, but in order to do that, you need to sort of dive into inside of the conducting material and look at that from a microscopic point of view, right? Okay, but we're going to just justify that internal structure. So let's assume that we have some conducting material in order to, again, as I said, in order to see what R can depend on. So we need to assume that there is some conductor or resistor, of course, which has some resistance, right? And it has some cross-sectional area. It has some length. Let's assume it has cylindrical shape, right? And now let's see what R can depend on. And let me give you this. Let's assume that I took a bunch of poles from the lab, basically optical, or poles from optical table. All right, so let's assume that we have these two resistors, or two conductors, right? Made of the same material. They have the same cross-sectional areas, but obviously they have different length. This is, of course, significantly longer than that one. So guess which one has larger resistance? Of course, everyone answer this question correctly, usually immediately, right? Because sort of gut's feeling tells you immediately that the longer resistor, the longer conductor, the larger resistance must be. And justification, explanation of this is very simple, because again, what's the nature of resistance? Nature of resistance, as I told you, right? Try to run along a straight line through the forest. Of course, you will experience you'll have lots of painful experience. So in order to describe that, we introduce resistance. And of course, similar electrons experience similar when they fly through the crystalline structure, right? So it's basically electron gets accelerated by the electric field, by the potential difference, right? So gets accelerated, collide with atom, right? Collision, concussion, recovery, right? And then again, acceleration, collision, concussion, recovery, after collision with the next atom, and then next atom, and so on. It's a gazillion number of collisions, right? It reminds me of American football. Sorry, guys, I like to make fun of American footballs. I'm a soccer fan, right? So, but American football is too rough for me, right? So I cannot watch it. So whenever I have a chance, I like to joke about that, right? But anyway, so you see, basically that's the nature of resistance. And of course, the longer a resistor is, the longer the resistor, the larger the resistance of that conductor, of that resistor, right? So obviously, if L is not L, okay, let's say if L is present in the expression for R, it must be in the numerator here. So R, our resistance, must be proportional to L. Of course, again, it's not a proof, right? It's sort of conceptual justification, conceptual explanations, right? Of course, I cannot say based on this that R is not proportional to square root of L and L to the power of 2. But of course, it can be derived. It can be derived. If you want, you can read the book, and I think derivation is there. I just want to justify it, right? I want to justify that L must be in the denominator. R must be proportional to L, right? Okay, so inside of R, there must be length of the conductor, or length of the resistor. You can call it resistor, conductor. It's conductor with some resistance. Okay, then next one. What if I give you this situation? What if I have two resistors like this? Now they are of the same length, made of the same material, but they have different cross sections. Right, you see, this one is significantly thicker, cross section is significantly larger than that one. So now the same question, which conductor, which of these resistors have larger resistance? Okay, usually these questions students start struggling, right? And they most of the time they pick the wrong answer actually. So which has larger resistance? They usually pick this one as the resistor which has larger resistance, but actually it's not true. Let me give you sort of like an everyday example to justify which answer should be the correct one. Imagine this situation. I don't know, rush hour. Okay, before the lockdown, right? Rush hour in Boston, right, around 8:30 a.m. somewhere in a subway downtown crossing platform, right? Subway. So you can easily imagine, right? So platform is filled with people, right? And so train comes, right? And first, what happens usually, right? So our small doors get open, right? And all these people start squeezing in. Lots of elbowing, pushing, right? Coffee being spilled, right? Lots of troubles, right? Lots of resistance to get into the train car, right? So that's what we usually experience on a train, right, in our life. And so, but let's imagine this situation. Okay, let me finish this example and then we'll have a break. But let's imagine this situation. What if in this better fairy tale world, train comes, again, the steel platform is filled with people, train comes, and in this train, just the whole front wall of the train car gets lifted. So what happens then? Now all these people, almost without any significant amount of resistance, will be just able to step in the train, right? Without any significant resistance. So you see, we increase the area, cross-sectional area, and now resistance is significantly smaller. So now it's easier for people to get in the train. So now, if you have not just these small doors, but a big door, now it will be much easier. So all these people will be just able to step in, and everyone will be happy. So you see, the larger cross-sectional area, the smaller resistance is. And this conclusion is not completely intuitive, right? Usually students have no troubles telling me this, but this conclusion is not that obvious. So, but anyway, you see, the area, cross-sectional area, must be where? Must be in the denominator of the expression for the resistance. So it must be, R must be proportional to 1 over A, where A is the cross-sectional area. So out of these two conductors, right? So this one with larger cross-sectional area has smaller resistance. So now we know that R should be proportional to L, length of the resistor, and inversely proportional to the cross-sectional area. So we assume that it has this cylindrical shape, right? So now the last parameter. What if, okay, I don't have two identical resistors made of different material, but you can easily imagine. Let's say I have two slides forward first. Let's say I have, wait, wrong direction. Two identical resistors, but one is made of, I know, aluminum. The other one is made of gold. What will happen in this case? Actually, nothing, right? I will just grab the gold, cash it, and get on out of here to have a nice vacation, right? But of course, you understand that different material. You understand or have God's feeling that obviously different material must have different resistance, right? You all know that sort of, yeah, from your everyday life, you've heard maybe that gold has a smaller resistance, for example, than aluminum, right? And so we need to include somehow the presence of the information about the material into the expression which I want to eventually write. Right, so we found that R is proportional to L, R is inversely proportional to the area, and now we need to insert into this equation somehow the presence of the material. Which material is this? Is it a gold, copper, or something else? And at this point, it's pretty much up to us how to introduce that parameter, new quantity. You can introduce it into the numerator or denominator, because not most of the time, all the time, that parameter is measured experimentally, right? And then people write reference books, and then you can open the book. Okay, so aluminum, it's this number. Copper, this number. I don't know, 50% of aluminum, 50% of copper, it's that number, right? So it's all tabulated. So pretty much it's up to us how to introduce this new quantity. We're going to use what is called the resistivity. And letter rho is used. Rho, Greek letter, and it's called resistivity. And resistivity enters into this equation into the numerator. And that's what we're going to use. So R will be proportional to rho. But sometimes, like for example, in the world of semiconductors, right, people find it more useful to introduce not rho, but a new parameter, conductivity, and it enters in the denominator. For them, it's slightly more convenient to use conductivity instead of resistivity. But people who work with circuitry, right, circuits, right, so for them, it's easier to use resistivity. Right? You see, it's up to us at this point where to introduce this parameter describing the material. So resistivity it's a property of a material. Gold, certain number. Copper, certain number. Aluminum, certain number. I don't know, some kind of steel, a certain number. And all of those numbers measured experimentally. You just hire a cheap labor, grad student, right? And he will be sitting measuring that all experimentally and filling up those tables, right? So eventually, now we can write finally the formula which can be used to calculate resistance of this cylindrically shaped resistor. So resistance R is equal to resistivity rho times length of the conductor or resistor and divided by its cross-sectional area. Right. So now, what's the major feature of this formula? I asked you exactly the same question a couple of classes ago. I think a couple of classes ago. You should still remember that. So what's the major, and then I will remind you in a second where I asked you before. What's the major feature of this formula? Does it depend on the electric current? No. Does it depend on the potential difference? No. Does it depend on the value of the current? No. Not a single electric quantity. It depends only on what? Rho describes the material. Then L, length, geometry. A, cross-sectional area, geometry. So basically, this resistance depends only on the material and geometry. So that's why, if again, if like in old days, if you go to Radio Shack, right, you can see resistors, a shelf with resistors, and they're all labeled. Actually, here in the United States, they use different colors, lines of different colors. For me, it's still confusing. I remember I tried to figure it out several times. Too complicated, too much, right? After some time, anyway, I forgot about that. For me, it's easier to write something like 15 ohms. Great, I can read, right? But those lines, I find it very confusing, right? Unless you work with that every day, then yeah, it's easier probably. But anyway, so that's why you can label all those resistors, because once you build it, it will be exactly the same. So it doesn't matter what's the potential difference you apply or what is the value of the current flowing through that resistor. Resistance is going to be exactly the same, right? Of course, assuming that you use that resistor in the working range, right? Of course, there are some limitations. Okay, and similar feature we saw where when we introduce, you remember, capacitance of a parallel plate capacitor. You see similar structure. Here we have rho material describing material. There we have epsilon naught describing again material between the plates. Of course, it was a vacuum, but if it was filled with some dielectric material, we would have epsilon. Again, some constant measured experimentally and tabulated. Open the reference book and find it. Then L over A geometry, and here A over D again geometry. You see lots of similar features. Right. Okay, so that's what we need, and units, yeah, just whatever you see in the formula, yeah, there will be some cancellations, and then you will see just ohms times meters. And now we, yeah, as I told you, also some people instead of rho they use sigma conductivity, and these two parameters depends. Okay, sigma equals 1 over rho, right? So reciprocal of resistivity, it's conductivity. Right? And again, as I said, it's people from the world of semiconductors, they prefer to work with conductivity. Then, now guys, resistance and resistivity sound so similar, and at the very beginning it can be confusing. But it's only at the very beginning. Then you'll get used to that and there will be no troubles, right? And again, I want to emphasize on their difference. Again, resistance is this, resistivity is that, rho. So the resistance, it's a property of a particular resistor, particular object, which is made out of certain material, which has some shape, cross-sectional area, some length. Resistance, it's a property of an object. Resistivity describes material. It doesn't care what's the shape, right? It just, okay, gold, this number, copper, this number, right? Resistivity, it's a property of a material. Resistance, property of an object, right? So that's the difference. And so here I copied and paste table from the book. Right, you see some common materials, and here the first column resistivity, ohms times meters, right, and you see the numbers, right, small 10 to the power of minus 8, 10 to the power of minus 8, right, and the second column is conductivity, which is a reciprocal of resistivity, and you see if you take the 1 over this number, you will end up with that number. Right? But again, in this course, we're going to use resistivity all the time, and for your homework problems, if you need a certain information about resistivity of a certain material, don't try to Google. Use this table, because mastering physics is programmed assuming that you use these numbers. Google can give you a slightly different number, right? I will not be surprised. So, and then of course you will have troubles solving the problem, because mastering physics will not accept it, right? It'll start giving you some start saying you that it's wrong and wrong and wrong. Right? Okay, so use this table. So that's what I was planning to discuss. And you know what? Just before before I switch to the whiteboard and before we start solving problems, again, I want to emphasize on one thing. Now we introduce resistance, right? R. And okay, resistor, right? Resistors. And now, in order to analyze, we are going to analyze those resistors, right? And in order to analyze resistors, you basically need to know, again, 3 parameters. I already mentioned about these 3 parameters, this circuit trinity, right? I called it. Resistance, current, and potential difference. Ri delta V. Similar things we saw when we introduced capacitance, right? Back then, we saw again 3 parameters: C, Q delta V. Now it's R I delta V. So again, 3 parameters. Once you know those 3 parameters, you can say that you basically know everything about a resistor. And similar thing we're going to see when we introduce inductors, right? And that will be in probably in a week and a half when we will be in the world of magnetism. Okay, so that's the lecture material, and I think now it's time to solve a few problems. Let me check it. Yeah, so now it's time to solve a few problems. Let me switch to the whiteboard. So the first problem, it's chapter 27, problem 11. 2711. Sounds familiar. No, it sounds like 7-Eleven, but it's a 2711. Right, so what do we have here? There is an integrated circuit. It sounds scary, right? But in this case, for us, in order to solve the problem, it's just a slab of a material. That's it. So it sounds fancy, it sounds scary, integrated circuit, but it's just for us, it's just a slab of material through which current flows. So, but anyway, let me write that down. It sounds cool, right? So we have an integrated circuit. And you know what? I will draw immediately, right? Because it will be easier then for me to say what is given. So let's say we have this cross section. And yeah, it's basically a slab of material. So let me draw it. And so this is A, this sort of this length, and this is B. And these A and B are given. So let me write A is 2.5 micrometers, micro again 10 to the power of -6. Then B is 75. B is 75 micrometers, right? And we know that current flows through this structure. Current flows, let's say this way. But information is given not about the electrical current, but about current density. And it's not unusual, especially in the world of, for example, semiconductor lasers where I worked. So if you read the paper, most of the time they give, when they try to describe their laser, right, fabricated laser, and describe the parameters, right, power, right, and how much power it generates, how much power you dump electrical power, right. So every time they give information about current density, because different groups, they fabricate lasers of slightly different size, right. So it's much more convenient to give current density. Then it's easier to compare results, right. So in this case also current density is given. I'm just telling you that it's a very common situation, right? So current density is given and it's a 75. Okay, let me just grab my notes. Times 10 to the power of 5. So current density J, it's a 75 times 10 to the power of 5 units, amps divided by meters to the power of 2 units of current, right? Yeah. Then what we need to find, okay, let me also write, so this is current density, right? So we need to find how much charge flows through this structure in 15 minutes stretch of time. Right. So what we need to find, let me write. So we need to find Q in delta T equals to 15 minutes. Okay, so that's the problem. And It's not that bad. It's not complex. Actually, today most of the problems are reasonably easy, and students have the least amount of troubles with these problems on the exam, just based on my experience. So, charge. Recall what we introduced today and yesterday, and where have we seen charge? Only in one place, only in one formula. In the definition of current. You remember current was introduced as the amount of charge per unit time. Again, crossing a certain cross section. So let's recall it. And again, we introduced current like this, instantaneous current as dq over dt. But in our case, observational time is not infinitesimally small. So of course, we're going to use the sort of average values. So I equals q divided by delta t, right? So we adjust it for our case. And plus, in our case, current is constant. So yeah, we can make this replacement. So that's current. I mean, that's the charge which we need to find. So let's just solve it for q equals to I times delta t. And now I will open my explanation box. And current is not given, right? But we should be able to find it easily because we have information about current density and we have information about basically cross section. In this case, it's a rectangular shape, so it's a times b, right? So I can write that current equals to j times. Okay, I will just use first a cross section, no cross sectional area. So I can write it j times a times b. Okay, let me close my explanation box. And so now I just need to plug it. And basically that's the solution, right? So you see it's simple a times b times delta t. But, of course you have to be careful. It's like in the question which we didn't poll, it was at the very beginning of the class, where I asked to calculate current, right? And we have something every minute, 120 coulomb of charge crossing a certain cross section, right? And we had to find current. And I told you, never use meters because otherwise you will mess up the units. And at the end, when you calculate current, you're not going to have amps. You're going to have some coulombs divided by meters, which is really, you will confuse the living day out of people who knows physics, who know physics, right? So of course we need to convert these to seconds, right? We need to convert these to seconds. All right. Okay, I will just write convert to seconds, but I'm not going to convert because at this point you should be able to convert minutes to seconds without any troubles, right? I will just write must be in seconds. Right. Okay, it should be enough. And of course, don't forget then that micro 10 to the power of -6. Again, because sometimes students are not very attentive to those prefixes, right? Micro 10 to the power of -6. All right. So of course I can frame it sort of, and if you plug numbers, the answer is going to be okay. So let me write q equals to 0.127 coulombs, because now we just found charge, units of charge, coulombs. Okay, basically that is the problem, but I added one additional question, because in your homework there will be a problem where this additional question will help. So I added additional question, how many electrons actually flow through this structure? Here we talked about charge, right? But of course, we know that each electron carries exactly the same amount of charge. They're like infinite number of twins, right? Exactly the same, right? In shape, in size, in charge, right? Everything the same, right? So the additional question is, how many electrons actually flow through this structure in this period of time of 15 minutes? right? And of course, once I pronounce what I just told you, right? So the answer, the solution is obvious. Since this charge is carried by identical objects, identical electrons, which has exactly the same amount of charge. So then it's very simple. You just need to take the total charge and divide it by the charge of one electron, and that will give you number of electrons flowing, right? So, okay, let me write first like this. So Q equals number of electrons times, which I charge use just E minus, okay, times E minus. E minus is a charge of one electron, right? So now, of course, N equals to charge divided by charge of one electron. So it's a 0.127 coulombs divided by 1.6 times 10 to the power of minus 19 coulombs. Of course, coulombs over coulombs give us nothing, as it should be, because number of particles doesn't have units. Right? So the answer is going to be 7.9 times 10 to the power of 17. That's number of electrons. In your homework, there will be some electrical device, I know, some electric fan or something like that, right? Or hair dryer, I don't remember. And at the end, you will have to find number of electrons flowing through that device. But first, you need to find charge, and then you can easily extract information about the number of particles. Okay, so that's the first problem number 1. The first one, but problem number 11. Okay, there is a chat information. Does E represents a number of, no, E minus, it's a charge of one electron. Okay, let me emphasize, so write this. E minus, it's a charge of one electron. Charge of an electron. Okay. So next one, problem 31. Still the same chapter, 27, 31. So in this problem, what do we have? 100-meter long gold wire. Lots of problems in this book are about gold. It looks like author likes gold. Actually, who doesn't like gold, right? What a silly statement, right? But anyway, 100 meters long gold. For you, it might sound kind of strange, but for example, not for example, every photonic center, director of any photonic center has somewhere in the safe some spool with gold wire, because they used it to fabricate some devices, right? To have a good contacts, right? So some lasers, right? So every time they use small amount of gold, right? So somewhere in the safe, director of photonic center all the time has something like that. So it's not unusual situation. So 100-meter gold wire, diameter is given, and then we connect it to some battery, and we will need to find the amount of current, and we need to find the current flowing to that structure. So let me draw the picture, and then I will write what is given. So, okay, gold wire, basically it's a spool, right? But I will just draw it something like this, just as a long cylinder, right? So let's say this will be my 100 meters long gold wire. And let me show that this length is 100. You know what? I think I probably use L. Yeah, first let me use symbol. Right, so L equals to 100 meters. Right. And diameter is given. Yeah. Let me show that this is D. Okay. And yeah, gold. It must be written over here. Let's say it's gold. And it is connected to a small battery. So delta V also is given. Okay, so now let me write everything. I mean, give you numbers. So we have a gold wire. So L is 100 meters, as I wrote, and diameter, the diameter is 0.1 millimeters. So that's information about the gold. And potential difference, 0.7 volts. You know what, let me write it here. Delta V. Actually, it's written, it's a watch battery, 0.7 volt. Very small voltage. So we need to find current. So what should we do? You know what? Again, let me just write everything that we can about this problem. Again, everything that we can from the point of view of physics, because you can describe it I don't know, in any way. If you have some artistic skills, it's beautiful, it's ugly, it's sophisticated, it's whatever, from the point of view of physics. Right? And again, we have basically a resistor. This gold wire is just a resistor, right? And we want to describe it, right? So we have again three parameters, R, I, delta V. So let me write everything that we can about these three parameters, and then actually we will solve the problem, right? Okay. Again, I will write something like I wrote when we discussed capacitors. Again, three parameters. So let's start with R. And actually R is not given, right? It's still a question mark. It's not the final question mark, right? Not the most important, because at the end we need to find current. But anyway, at some point, of course, we will have to find resistance, right? It's not given. And you remember, it depends on the geometry, right? And do we have enough information about geometry in order to find resistance? Yes. We have cylindrical shape, our wire, right? We have length, we have diameter. So basically, we should be able to calculate cross-sectional area. And we also know that material made of gold. So pretty much we can discuss the formula which we just introduced 5 minutes ago, right? So in order to, of course, to use that formula, we will have to look at those tables, at that table, in order to find resistivity, right? Resistivity right now in the problem is not given, but of course you know where to find it. Open the book and see that number. But of course you need to realize, since material is given gold, yeah, we can find that resistivity. Right, so let me write. So since geometry is given, so it means using this formula we should be able to find resistance. Rho times L divided by A. So that's what we can get about resistance, right? Then second parameter, what? Current. Current, it's our goal. That's our goal eventually, right? Then what else? Potential difference. Potential difference is given. And so pretty much that's what we have. And of course, we'll have to use a formula which connects all these three parameters, which is Ohm's law, right? R equals delta V over I, right? So that's what we can extract about these three parameters. Right? Okay, so now let's solve it. Again, basically solution will consist of usage of this formula, okay, collaboration of this formula with that one. Right? That's it. Um, so first, resistivity. Again, from the table, resistivity is, let me write, where is that? It's a 2.4 times 10 to the power of minus 8 ohms times meters. And that's, you can get from table, which table? 27.2. 27.2. For gold. Okay, so now let's first find resistance and then current. So resistance will be, of course, rho L over A. All right, rho L. Okay, commonplace, reasonably commonplace for completely unnecessary mistakes. Diameter is given, so you need to carefully calculate area over a circle, right? So it will be pi. Of course, if radius is given, it will be pi r squared, but since we have diameter, so we need to take d over 2 to the power of 2. Pi times d over 2 to the power of 2. Pi d squared over 4. I don't know why, but plenty of students have troubles with these simple formulas for circumference, areas, volumes. Okay, so now let me write it. So it will be 4 rho L divided by pi d to the power of 2. And of course, d must be in meters, right? So right now it's given in millimeters. Let me convert it immediately into meters. So it will be 0.1 times 10 to the power of minus 3 meters. Of course, in meters. D must be in meters over here. Right? L is in meters, so everything is good. So no troubles in the rest of the spots. So now I can write down the answer. It will be 305.6. We found resistance, so it's just ohms. Okay, so now once you know resistance, of course, you can find current easily from the Ohm's law. So I, it will be delta V divided by resistance. So resistance we found, delta V is given, piece of cake. So it will be 0.7 volts divided by this 305.6 ohms. So the answer is, where are my notes? 2.3 milliamps. 2.3 milliamps. Yeah, reasonably small current. You see, it's not complicated at all, and I told you, usually if I give a problem, something like this on the exam, the least amount of problems. Most of the students do very well on this. Okay, so now we still have almost 15 minutes. Great. Now, more or less like a conceptual question. Next, a few. Okay, it looks like a chat activity. No, it's still the previous one. The system didn't drop the sign. Okay, this next one is actually from the Stop to Think. If you read the book, so occasionally there is a small sort of section like a Stop to Think, stop thinking, right? Where something is discussed. So I picked one of those places to discuss here. It's similar to the conceptual question which we had in our lecture. So let me write. It's Stop to Think 27.4. We put small bullets, so it's it's like, it sounds I'm making fun of this title because if you read physics book, you think all the time. You don't have to stop to think, right, when you read physics book. That's why I'm making fun of this Stop to Think. 27.4. It's not a novel, it's a physics book, right? So what do we have here? We have a junction point, complicated junction point with 5 wires. Right, so let's draw it. Right, so let's say we have one wire, second one, the third one, the fourth one, and the fifth one. Like a complicated intersection. Right? And currents are given. 3 amps here, 2 amps in this wire, then 4 amps in this one. How much? Yeah, 4. And that one, 6 amps. And of course, in this wire, we don't know. I sub x with a question mark. So we need to find the amount of current in this wire and the direction. It's sort of almost like our clicker question, but of course now our situation is more complicated, right? So, but the approach is very similar. Like I told you. First of all, about the direction, we know it's either up or down in this wire. So, in order to use, and of course we'll have to use conservation of current in the presence of this junction point, right? So let me write. So of course we will use conservation of current first of all. Conservation of current, which is total amount of current entering must be equal to the total amount of current leaving junction point, right? So now we just need to apply it. And again, in order to apply it properly, we need to make a decision where this unknown current will be on this side or on that side. If I assume that current direction this way, then of course it will appear on here. If I assume that my unknown current is that way, it will appear on this side of the equation. But we have to make a decision. We have to guess. But again, guessing, it doesn't sound cool. We have to assume. Let's assume a current direction. Our unknown current direction. Which one I assumed? I assumed that Ix is out. It means down. Okay, so I just follow my notes. So, and I will use different colors. So assume Ix is out. Out, it means out of the junction point. But in this case, of course, sort of graphical, it means it will be down. So in this case, if it's out, so it will be on that side. And so left-hand side will be what? 3 in, 4 in. That's it, right? So it will be so 3 amps in, then 4 amps current also in. So only there are 2 currents, and the rest of the currents will be on the right-hand side, on the outside. 6 plus 2 and plus our unknown. You know what? Since I assumed it, let me draw in blue. So that's my assumption. So it will be, what did I say? So 6 amps plus 2 amps and plus our unknown current x, I sub x. So of course, we can solve it for I sub x, and that will be equal to what? 7 on this side, 8 on that side. So it will be I sub x -1. Let me check. Yeah, -1. So -1 amp of current. Okay, so now we have to say something. It means that absolute value of current I sub x is 1 amp, and minus, it just indicates that my assumption was wrong. So I'm not going to buy a lottery, right? So I'm not good at guessing, right? So it means that I can write, so I sub x 1 amp. That's the, okay, doesn't look like 1 amp, and it is in. And which way I wrote? And it's in, not out. So this is the wrong direction, right? And as I told you, we're going to use this trick assuming current directions. I want to say often, when we're going to discuss circuits, we're going to use this trick often, because after a few days we will move into the world of magnetism, and there we will actually we will be still using currents, right? But I don't think that we will be using this trick. So next one. Okay, it's just to remind you one more time about this procedure, because very similar we had in our clicker question. So after this, you should be okay with problems like this. You know what? The next one, I will probably use still this whiteboard. I thought about skipping it, and then I decided no, I will keep it. So the next one is conceptual question 9 from the book. So I will put here the bullet CQ, conceptual question 9. And there are parts A, and there's a part A and B. So we have a wire of this shape. So first, of different cross-sectional areas. So this is section 1, and this is okay part of the wire 1, and that is okay section 2. And of course there is a current flowing through the structure. And there are two questions. Simple, right? That's why it is conceptual. So first we need to compare currents. We compare, actually it's a part A. Part A, compare I current in the first part and current in the second part. So what can you say about these two currents? And I think at this point everyone is already aware and know that it doesn't matter what happens with the wire. It can be twisted, bent, right? Have different cross-sectional areas, right? If there is no junction point, or there are no junction points, current must be the same. It doesn't matter where you measure. Here, here, here. You can take any cross-section, and current must be the same. It's like I compared with the situation of water flowing through a pipe of this shape. So current must be the same. So okay, equal. But in part B, what about current densities? Current densities. Again, compare now current density. So now J1 and J2. Which one is larger? Oh, smaller, right? So now we have to be careful, and here students start making mistakes. Usually, when we were at school, right, and I gave a quiz like this in the class, right, 10 minutes quiz. No troubles here, and students start having troubles over there. But again, it's still quite simple, because we just need to remember definition of current density. Current density, it's you take the current and divide that by the cross-sectional area through which this current flows. Right. So obviously, in the first case, this is right. So it's I. Okay, let me write J1 equals to I, which is the same, divided by A1, and here A1, right? And the second current density, it's a current divided by A2. Since A1 here, I can even write, so it's this is A1, and here it's a A2. Since A1 is smaller and it's in the denominator, so current density 1 must be larger than current density in the second section. Right? And probably I will write underneath, since A1 is smaller than A2. Since A1 is smaller than A2. So with current densities, we have to be a little bit more careful. But currents, it doesn't matter. If there is no junction point, then current must be exactly the same. Okay, we still have a couple of minutes. I think it's clear, right? Let me quickly discuss the next. It's actually the problem, but it's worth of just a conceptual, being called a conceptual question. It's a problem 15. So what if we have this wire of this cross-sectional area? All right, so the material is over here. And radii, let me call it A, and this is B. So, and current is given. Current is, okay, I'm not going to use numbers. I will just use symbols, I. So we need to find current density in this case. What about current density? So you see, basically we have a wire with concentric hole. Maybe I can draw here a dashed line, emphasizing that this is hole goes through the structure. So how can we find current density? Again, definition of the current density, by definition, it's what? It's a current divided by what? The cross-sectional area through which that current flows. So it's basically area, this highlighted area. So how can we find that highlighted area? Okay, I can draw a cross section. So if you have something like this, right? So how can you find area of this structure? You take, okay, let me hold you extra half a minute. So you take this area of this object, the whole circle, and subtract the area minus area of that whole, right? So in this case, it's a in terms of our notation, so it's an area of okay, the area which we want to find, area equals, so it's a area with radius a, no, b, in our case b. It's an area with radius b, so it's a b, and this is a, right? It's an area with radius b minus area with radius a. So this is the area through which our current flows. So that's what must be here. So it will be total current divided by a sub b minus a sub a. So of course, if you write explicitly using the formula, so it will be pi b squared minus a squared. That's it. And when we will be in the world of magnetism and when we will introduce Ampere's law, we will be using this a lot. And still, every semester, lots of students struggle with finding these current densities and then calculating the current within a certain radius and so on and so forth, right? So that's why I usually prefer to discuss these questions like as a preparation to that moment. Okay, guys, that's it for today.